with our final presentation here of the day. Dr. Jared Smith, Doctor, I hope I got that right. All right. Dr. Smith, EIT, is a machine learning specialist in the U.S. Geological Survey Water Resources Mission Area. He's got a background in environmental systems engineering, spatial data analysis, and statistics. His previous research has coupled physical and mathematical models with statistical analysis to inform planning and management decisions for environmental, earth energy, and water resources system. His presentation will be discovering flood regions and predicting flood flow metrics to inform bridge scour studies in the U.S. Let's welcome Dr. Smith.
All right, I'll get this presentation up. So we'll be going from really small scale to national scale, so a little bit change in scope. All right, great. So I'm Jared Smith. I'm with the USGS, and this is a project that's funded through the Federal Highways Administration. And if you saw Cornell's presentation, this is related to the flood flow metrics and flood flow durations that can be fed into those Scour models that he was showing. So this work is to discover flood regions and predict flood flow metrics to inform bridge scour studies in the conterminous U.S. Okay, so motivation for this: bridge design and scour studies require accurate flood flow information that includes the magnitudes and durations, like I was just saying. And the bridges can be located over ungauged reaches, so those estimated flows are needed for models for those ungauged reaches. And that's where our work is coming in. We're trying to predict flood flow metrics for gauged sites as well as ungauged sites. So, but the potential challenge here for developing flood flow prediction models is that the flood generating mechanisms are actually different across the United States. So we can think about rainfall dominated, hurricane driven flood in one part of the country on the eastern coast, and we can think about snowmelt driven floods that are in the Rockies or something like that. And so what we want to do is to discover regions in the United States that have different flood flow generating mechanisms so that we can develop better models within those regions to predict those metrics. And so what I'll show in this study is both the classification work to come up with regions of the country with potentially different generating mechanisms for floods, and then models that can predict the flood flow metrics within each of those regions. And one of the more science questions for us in developing these modules is, can we develop a model in, say, a rainfall-dominated region, transfer that model structure into prediction in another region that's, say, snowmelt-dominated? And so I'll do that in evaluation in this presentation. Start off with just the flow data that we were working with for this study. We wanted to focus on minimally altered catchments in the US, and the motivation there is that those sites would then be more driven by climatic signatures, and so then we could come up with more generating mechanisms that are driven by climate, as opposed to things like land cover change. And so for this work, we have a requirement that we have at least 20 years of complete data to work with. And that gave us about 1,380 sites that are plotted in this map here from the Gauges database. Gauges 2 is an assessment from the USGS, the product from the USGS, that provides sites that are reference sites that are so-called minimally altered. They don't have management involved, management actions and line cover change, et cetera. And it also has a non-reference site, which we didn't use for this particular study, but could in the future. And also overlain there are the ecoregions, and ecoregions are generated just for reference, just to see. Those are sites that have been identified as having different ecologically relevant distinctions. Okay, so what are we actually working with to predict? I mentioned flood flow metrics, so we actually compute 4 different metrics for each different quantile magnitude. The magnitude in this figure here is the red dashed line, just for reference, and the y-axis is stream flow, and blue is a hypothetical response that you might get from several storms that come through over the period of record on the x-axis. And so the first metric is the frequency. That's just the amount of events that are above that magnitude threshold. Then we have the duration, which is how long those events last. The peak flow, which is the maximum stream flow observed for that. And then the flow volume, the integrated volume under that event. So for the individual metrics, we compute the average over the entire period of record. And so that gives us a sense of the long-term behavior for each of these metrics. And what we wanted to do for these, you might think about the timing of when are the events happening in the calendar year, and that's an indication of how those floods are being generated. So what we did was to look at each of those flow metrics over each of the water year seasons, shown in here split October, November, December, January, February, March, et cetera. And so we can then look at what are the values of those metrics in each of the seasons, take the average over all the years that we have on record, and then get a normalized so-called fingerprint for each site. And one way to interpret this is, say if this is frequency, then we have about 50% of the events generated in the January, February, March for this particular site. And so you can get a sense for, okay, events that are generating floods are mostly happening in that January, February, March period. And we can do that for all of the gauges across the country to have the fingerprinting for all those sites. And what do we want to do with that is to identify those regions, and the way we did that is through cluster analysis. And I'll give an overview of what cluster analysis is for those that are not familiar. This is a type of unsupervised machine learning, and it's discovering clusters or groups of gauges that have similar characteristics. And in our case, we were looking at these metrics, and they all have different characteristics. So we could say that the x-axis is the frequency, the y-axis is duration, and then we plot our gauges in certain locations, and maybe they come out hypothetically looking like this. And that'd be really great. That's well-defined 3 clusters there, right? And so we can plot the gauges and look at them in a similarity space. And so we can have numbers of gauges on the top, and then as you go down this diagram, eventually these branches are merging to get to a similar cluster. And in our case, like I said, we have hypothetically, for this example, 3 clusters that are plotted in this diagram like this, and they split out really nice. So we hope that we could do something like that to get gauges and regions across the country. And so what we did is we asked this question of how similar are the seasonal patterns for each of these flow metrics that we are looking at. And that again, for us, would mean that we take the seasons, and x1, x2, x3, x4 in our axes are each of those seasons, and we do that for all of the possible metrics to get quite a large assessment of variables to be working with to evaluate those similarities. And just to summarize what all that would mean, we have 4 seasonal flow metrics: the frequency, duration, maximum flow, and flow volume. And then we can look at several different magnitude quantiles. And for this work, or this presentation, I'll do 75th through 95th in 5% increments, but we've done down to the median for higher flow, or mid-high flow and high flow categories. And that gives us a total dimension to cluster on for 4 seasons, 4 flow metrics, 5 quantiles, and that's 80 different variables to be looking at. And that 80, again, is the fingerprinting for each gauge. We have 80 of those for each site, and then we try to figure out how similar those are. And when we throw that into this cluster algorithm and then process the results, we get a map that looks like this for the United States. So we get spatial clusters appearing, but we didn't actually provide any spatial information to the algorithms. That's, to us, really cool as a result. Like, what we're seeing from the fingerprinting is that, okay, sites that are similar to each other tend to be in spatial clusters with each other, and that's just from their hydrological signatures. And we can then label those regions based on what processes that we find in those regions. So in region 1 and 4, which are both on the left here, those are both more snowmelt-dominated regions. One of them has higher snowpack. And then on region 2 is the top middle. That's a more rainfall-dominated region. Region 3 is more Gulf Coast storms, and as storms from the Gulf migrate, they tend to go up through the Midwest there. That's the pattern that we're seeing there. And then region 5 is atmospheric river Pacific coast processes. So just at broad scale, we feel pretty good about the resulting clusters that came from this algorithm. And further work will go into more time series analysis and looking at more detail at individual sites in here. So that's the first step. So we have these clusters, but we still want to develop prediction algorithms for sites within these clusters. So then that would allow us to predict in ungauged locations. So what the first step here is to first select what regions we want to work with. And the regions we looked at were the rainfall-dominated eastern US. So you see this pattern in flow volume that mimics the seasonal rainfall pattern. And then a snowmelt-dominated Rocky Mountain region, which we see a real big spike in the spring, April, May, June, during the snowmelt period in flow. So processes are different, likely different, generating the floods in these two regions. And to give you the sense of what the actual variables look like, in this case, for the presentation, I'll show a prediction of long-term average 90th percentile flow volume. And we have for the eastern United States a range from about 0 to 100 in flows across this in CFS normalized by drainage area. And then for the Rocky Mountains, larger upper scale here, ranging to about 250 on the high end, CFS per drainage area. And what I want to point out is that we were clustering on timing mechanisms for these frequency duration, volume, but we do still see variability within the flow volume across the region. So that's good for developing prediction model. We do want to see some variability. So like if we only had a constant value, then we would not really have much variation to be able to predict from an algorithm. From a regression model, for example. Okay, so the prediction experiment here, first step was what attributes are we going to use to make predictions for the flow metrics. These were watershed attributes that were gathered from nationally available data sets. We had about 150 attributes that were collected that are summarized in this table, include soil and rock properties, meteorologic drivers, land cover, all long-term properties, because we're looking over multi-decadal, potentially multi-decadal timescales for each of these sites. And those are collected for the immediate catchment as well as the total upstream contributing area. And you might be thinking, okay, that'd be a lot to throw into a regression model, right? That'd be about, in aggregate, 150 different variables. How do you select what to use? And what we initially did to screen attributes was apply something that's a type of screening algorithm called the Baruta random forest. And what you should take away here is it's just trying to get what information is likely not important for predicting the flow volume. And so in red here in this figure are attributes that were not important based on this approach. And then in green were the ones that were important. And the way this worked, just really briefly, is you can think about if you try to spatially randomize information, basically throw noise attributes into a model, those shouldn't come out as important. And what's location of that is around this yellow region in the diagram. And so where we think, okay, that's the maximum random feature, which is so-called a shadow feature in this approach. Anything that's less than that within the uncertainty of that can be considered as not important for prediction. Okay, so that allowed us to get a set of attributes that we could use in the model. And what model are we using? I'm a machine learning specialist, so I'm going to try to break down what random forest actually means here in a simple way. So if you think about a decision tree, at each one of these nodes, there's some split that happens. And say the top node here is maybe precipitation is less than 10 inches per hour or something like that. And then you go one direction if you have yes, and the other direction if you have no. You can just keep building out the tree with those different attributes that you have as inputs, and then eventually you build out a tree and get to a prediction. And you can do that with many different trees to get many different predictions that potentially have different attributes in each split. And in this particular algorithm random forest, the attributes are randomly selected each time for what to use. So you get many different trees in this forest, and then you can average them, ensemble average them, to get a prediction of what those the flow metrics are. And with any regression approach, you can think about, okay, it has parameters. Like if you have a statistical regression, you have coefficients, and in this you have those same kind of idea. You have parameters that can be changed. And you can have different number of trees. You can do 100, you can do 1,000. You have different number of attributes that can be randomly split at each point, and you have different number of observations that can end up in each of the bottom points of the trees. And so for our actual experiment, what I was saying earlier, we're trying to evaluate transferability from one region, a rainfall-dominated and snowmelt-dominated, to another region, and vice versa. So what we have are those two regions. We have gauges in both of those regions, and then we have gauges in all of the country that we could use. And for the actual algorithm, to train that, we can think about, you have all the data available, but you want to know, okay, if we use all those data, we won't be able to really validate how well the model is going to do. So we actually do 80% of the data that's available, and then train it on test on the other 20% to see how well that additional model that we had compares to the held out or not data that was not used for model building. And then we test again on the rainfall dominated and snowmelt dominated testing data. So I'll show results first for the rainfall dominated region. This is again for flow volume with events greater than 90th percentile flow. And what we see here is that, firstly, that what stands out really quickly is that on the x-axis we have the different training regions, the rainfall dominated, snowmelt dominated, the rain and snow, and then all of CONUS. And then on the y-axis we have the root mean square error of prediction. So you want to be low on this diagram. And for the model that was trained only in that snowmelt dominated region, it doesn't have good transferability into the rainfall dominated region. And so that would indicate that the processes that are important for that snow region are not necessarily the same as the ones in the rainfall dominated region. And then second thing to note is what's in the bullet here is that models that are trained in the rainfall dominated region are the best for that region. And when we add in additional gauges from the rainfall and snowmelt, so both regions together, and then considering everything in CONUS, those models do better than if we only did the snowmelt, but they aren't as good as training only in the rainfall-dominated region. And then this is now switching into that snowmelt-dominated region, where we see, again, similar result that if we go from the models trained only in that rainfall-dominated and then transfer into the snowmelt-dominated, that rainfall-dominated region actually does much worse. And then adding in additional sites from the rainfall and then all of CONUS, that helps significantly reduce from only doing rainfall, but it's not quite as good as training only in the snowmelt. And then second thing to note, you probably see the root mean square error bars are much higher in this, even though the scale is similar. But that indicates that overall performance for predicting the snowmelt-dominated region was worse. So what are the actual predictions that are driving these results? So we look at these so-called attribute importance plots for each the rainfall and snowmelt dominated region. And for the rainfall region, it's pretty much how much does it rain in total that is predicting this. So we have annual flow conditions, December, January, November precipitation, and April precipitation. So we see most of the months of the year coming up here as the top importance. And then for the snowmelt-dominated region, we see groundwater recharge become important, and then winter precipitation and snow become important. So this is indicating to us, at least, that processes that we'd expect to be important in each of these are actually coming out as important in the regression model. And I have a sub-note here that there's these CAT and ACC attributes. This is just standing for catchment, being the immediate catchment where the stream is, and then ACC accumulated from everywhere upstream as well. All right, so what do the residuals from these models look like? How well they look? Does it look like there's any spatial correlation? So for the rainfall-dominated region, we see this pattern. It looks fairly random by eye, at least, and we ran some tests of spatial correlation here. It looks like it's pretty well random, spatially random, which is good. That's what we'd want from any kind of model. And then for the Rocky Mountain region, similarly, we again don't see too much of a clustering of either the high or low residuals here. And note that the scale is quite different. So we see on the rainfall-dominated region, plus or minus about 2 CFS per drainage area, and then on the snowmelt-dominated region, plus or minus 20. So order of magnitude difference in ability to predict flow volume, which is of note and of importance here. That's the same. All right, so I'm just going to try to wrap up the results of this work and try to wrap it into relevance for design too. So just to summarize, there was initial cluster analysis applied for different flood response characteristics, and that provided geographic clusters across the United States, even though no spatial information was provided to our algorithm to do that. And that leads us to believe that the processes that are generating the floods in those regions are actually important and hydrologically important. So we then developed random forest regression models and trained them in a rainfall and snowmelt-dominated region or cluster. And those models that were trained in those perform better than models that were trained using all of the available data. And that, to us, suggests that, again, those clusters are providing hydrologically important distinctions within each of those regions. And for us, the next steps are determine which ungauged reaches are within each of the different clusters, and then predicting flood flow metrics for each of those reaches so that you could use them in a Scour study in each of those reaches, even though there are no gauges there. And of course, that will be coming with uncertainty associated with it as well. And that's the motivation for this work, is really to take what metrics we have predicted for the volume, the magnitude, the duration, and then be able to apply that where you might want to design a new bridge or evaluate a current bridge for Scour. So with that, I'm going to wrap it up, and I'll take any questions. Yeah, go ahead.
So I live in an area that's snowfall dominated or snowmelt dominated, and so that high variability makes it difficult to assess the flow or the runoff with these regression-based models, because we have such a huge interval that we're looking at. So have you looked into each cluster to see if there's subclusters within those to where we could be able to get that to be a little bit smaller? Because sometimes I have, plus or minus 300% for the upper prediction interval and lower one, and I'm still trying to evaluate what I should recommend for that 100-year flow within that range.
Yeah, we've looked into further so-called depths of the tree. I'll go back to the hypothetical cluster slide so you get a visual while I'm saying this. So, all right, firstly, we selected 5, and that was so-called optimal for the algorithm, or around the optimal for the algorithm, and then coupled with our physical process understanding was helpful. But there are further clusters that we could go. So in this top diagram here, the further you go down the tree, the fewer clusters that you get. But you could actually go up and cut a line somewhere else and get a different number of clusters. So within each of the regions that we show here, there are subclusters, like you were just suggesting that there would be. And to answer the question, we haven't done a detailed analysis of that, but it is possible to go from the results that we have into a smaller and smaller region and then see if we can develop even better predictions for those. So I hope that answers the question.
No, it does. It's helpful. And I guess ultimately, how are we going to be able to access this research for our use in the future? Because one of the problems we run into with just the spatially referenced gauges is that we find there's a lot of areas that might be close to each other that are really different hydrologically. So
Yeah.
I feel like this is a really great approach for solving some of those bigger problems.
Yeah, that's a great comment too. And so I didn't mention how we're going to release it yet. And I guess we're still in discussion. I don't know if Cornell and James are in the room, but we're still in discussion about how exactly to release it. But stream stats has been discussed internally as our likely way to release it. And so that would be hopefully familiar to most people in the room. It seems like that comes up often in conversations here. So That's
And then you've
that's
got
the plan.
research paper to support it.
Oh,
so
yeah.
you Go back and dig through all of those.
Yep. Yep. Go ahead.
So within those 5 groups, spatial groups, how do you, is there a way that you can cut it to see kind of like, especially in the top one, where it is so spatially varied, even though there's no spatial information, to say like how different attributes might affect it? Like she was saying, they might be they're spread out, but how do you make sure that there's something within there that's not super different that might impact it?
Is that going maybe more to the importance plots here, where we get to what is actually causing predictions? Yeah. So we have done this for each of these regions, and I guess relating it to the actual time series of flow that's happening is a future part of future work for us. But at the broad scale of what processes are affecting predictions in each of these regions, I guess this gave us some comfort about at least similarity, but there can be specific areas for higher residuals or lower residuals. That's partly motivation for this next slide, is looking at, are there spots that are coming out as particularly troublesome? And I guess in this case, maybe some in the Pacific Northwest might be a little bit different. And so I hope I said it in the beginning, but this is still in the works. And yeah, so that's part of our future analysis. Yep, go ahead.
We talked before, and I raised the possibility that you essentially apply this methodology to actually, instead of looking at the higher side, looking at the lower side of the gauge station. Have you thought about that anymore?
Yeah, we actually have done it, Joe. So that's in the analysis workflow. So there's another project that's loosely associated with this one. It's called the EcoFlows project at USGS, and that's largely focused on lower flow magnitude. And after we did this analysis for high flows, they came to us and asked pretty much the same question as Joe asked, which was, can we use this for determining low flow clusters? And so we tried that out, and it's preliminary still, but we can definitely talk about that later. I have my computer and I can show some results. So yes is the answer.
There's no other questions, let's thank Jared.